what else we can do, because I mean, I don't have any other boards other than what we've, huh? What is it? Yeah, I mean, you can use any. I mean, the one that I'm using is version 2021, and it should work still, but I think everything's written for 2025. Yeah, 2021. All right. So what we're going to talk about today is kind of what we're going to do in the next project, which is going to be a bit more advanced. So far, project one, all you had to do was just put like hardware on the board, but now we're going to start actually tying into what we've been teaching all this time. We've taught you about different processors, what kind of memory exists, what type of things might be on an SoC. When we're using our Urbana board, we're limited by certain things, such as, what type of stuff do we have on the FPGA fabric itself. If we had a much bigger FPGA, I don't know if you've ever seen like those big ultra scales and stuff, they might have more things like actual, RAM or all these components that we've talked about before. The Urbana doesn't have that, so I kind of want to go over, how we're going to implement a system on chip on the Urbana board, which actually is not a real SoC because there is no processor on it, right? And so we're going to see, well, how do we actually design it and turn it into an SoC? So I just wanted to remind you guys what is on an SoC. We have the processor, which is just the brain. We've talked about different types of processors, and we'll get into what we're going to use next. There's the memory. Okay, so where does the processor read its instructions? Where is its main memory? So it's RAM. And then the peripherals. So in our case, for our project, or in our class, we have the board here. It has a bunch of stuff attached to it. It's got like Wi-Fi cards, SD cards, USB stuff. Those are peripherals. Of course, they don't work unless you design your hardware to actually interface with those, right? Right now, the board in like a off state doesn't do anything unless you program it to do so. Okay, so for our FPGA, which is a Spartan 7, there is no processor on it. All it's got are LUTs, lookup tables, and it's got block RAM, and that's basically, I mean, there's some other stuff on there, but that's basically it. So how do we put a processor on here? Is there any way? Because we don't have a processor on the actual chip. So what do we do? So what we do is we use these things called soft core processors. All right. And a soft core processor emulates the behavior of a real processor, right? But it's actually implemented right onto the FPGA fabric. So, I mean, some of you guys have taken reconfig 1 or maybe reconfig 2, I don't know. But, you learn about what lookup tables, how they work on the FPGA. And maybe I think if, the undergrad students, you've taken digital logic, you had to design your own custom CPU, digital design. I think if you did MIPS, it's something like that. It's the exact same idea for the microblaze. It's a processor that was built by Xilinx that we're allowed to use, and it's very heavily optimized to use as little resources as possible, right? Because there are only a finite amount of lookup tables that we've got on the FPGA. So if we placed a processor, like a full-fledged processor that can run code, well, don't you think it would take up all of the resources on the board, on the FPGA? Well, it doesn't. And we can actually look at the resource usage with this, but it's heavily optimized for that, okay? And so I wanted to ask you guys, because we're not using a processor that's on the FPGA fabric, and instead we're implementing it through lookup tables, what are some of the downsides to this, like implementation, in terms of speed, maybe power consumption? What do you guys think? Do you think it's going to be faster than a processor that's purpose-built on the FPGA fabric? No. Yeah, so again, it's going to be slower because there is some type of delay that we have to consider when we put a microprocessor on. So when we put a microprocessor and implement it in this way, right? In terms of power consumption, it's not going to be as efficient, right? When you have an ASIC that's designed specifically for a specific purpose, it's going to use a lot less power than something like this, which is designed to be general purpose. But of course, the advantage is that it's going to be flexible. All right. And this isn't the only type of processor that you can use on the FPGA. Xilinx actually allows you to put ARM Cortex processors on our FPGA. However, they're not going to be as efficient for our FPGA uses. This one is designed specifically to use as little lookup tables as possible. So as little resources on the FPGA. And that gives us more space to put more peripherals on our board, on our system on chip. right? But if you want to use an ARM Cortex for whatever reason, you can. It's in the IP repo on Vivado, so you can use it. But again, you just have to remember if you do that, you have less space to put other things on it. So once we put the processor on the FPGA, and again, you will be doing this in your next project, which I'll probably release, I don't know, on Monday or something. This is exactly what you're going to be doing. So I'm just kind of telling you like what it's doing, and then I'll give you instructions on how to implement it. So when you communicate with peripherals, have all of you guys taken like microprocessors with Dr. Schwartz? Maybe not everybody, but you guys wrote code. You wrote assembly code or C code to access peripherals on the whatever the board was called, the micro pad, right? To control LEDs with software, or to control input or to read from input switches with software. And it works the exact same way on our design. We have a region of main memory that our microprocessor uses. Some of that is for, and this is just some general picture I found, but some of it is for like instructions, hosting instructions, and some regions, which in this case is like the green area, that's like mapped to peripherals, such that when you write to a specific memory address, like let's say that I say that the LEDs on my board are mapped to the first address in the peripheral region. If you write some value to it, then our system will kind of read from that area in memory. Well, really what happens is when you send a request to write to that address, our AXI controller and everything that you'll get into, like I think in the next lecture, all of that will handle sending that request directly to the LEDs rather than actually writing something into memory, right? But it just makes the interface super easy because then us as a programmer, all I have to do is just do a normal memory address write. I just say, I want to write to this address, and it actually controls LEDs. If I want to write to somewhere else in the memory, it works the exact same way, same functions, right? So the big thing here, and this is called memory mapped I/O, right? Where you're actually mapping like physical things into a region of memory. This is great because we don't have to really think about all of our components being directly mapped to the CPU. Because if you really think about it, if you've got so many peripherals like switches, LEDs, the only other way to do it is if you were to like hook up everything directly to the CPU and like check every single device that you've got, all at the same time. And that's really inefficient. So doing this makes everything simple. The AXI interconnect, which is something that you'll get into, will route requests for you. So all you have to do again is just write to the address where you said my LEDs are located. The LEDs will then look at that value basically, or the AXI controller will look at that and then turn on the LEDs accordingly. All right. So here's a code example of what something will look like in your next project. You're going to basically put a microprocessor, the microblaze, on the FPGA, and then you're going to hook it up to a GPIO component. And in this case, we have two different GPIO components. There's switches and LEDs. Now, a normal circuit would take those switches and just like, let's say that the switch on the left side is on, then the LED is turning on. The corresponding LED is turning on. That's basically what this program is doing, right? So in a normal breadboard, you might just hook them up directly, switch, LED, and then power and ground, right? Now, in this case, what we're actually doing is we're first sending a request from the microprocessor saying, hey, write to the address or read from the address that the switches are located or where they're mapped to. And then it gives us this variable, the switch data, okay? And so we use that to then say, okay, let's see what let's take this data from the switches that I see. And again, if you have switches on the board, let's say we actually use the Urbana board here. Let's say that we have 16 switches, right? That's 16 bits. Okay, so that's what, 2 bytes. So we could map this to 2 bytes of memory. All right, and when we turn up some switches here, this maps to some 16-bit value, and then that will be read directly into this variable switch data. Okay, so literally the physical way that we've moved the switches, because they're memory mapped, it'll automatically be read into that variable there, and then we can use that in our software. The next thing that we do is we assign the address where the LEDs are located. So again, like these LEDs on the board, what we do is we assign and write to that address, and we say that, okay, the LEDs that the LEDs, we want them to match exactly the pattern that the switches are on. So let's say the switch is on, the corresponding LED is on. So we just assign the LED variable to whatever the switch's values it is, whatever that 16-bit value is. And then we write to that memory address, right? We write to the memory address where the LEDs are on, and the microprocessor will handle that request for you, and then they will turn on. So basically what we've done is we've mapped our switches to the LEDs, but we didn't have to do any manual wiring of our stuff. And so this is a huge advantage, right? This saves you a lot of time. And again, you've done this in microprocessors applications, but back then you just had a board that worked, right? You just had the software that already exists, or you had the hardware that already existed. You just put on those backpacks and you just wrote to a memory address that was given to you. When we design our project, you can actually choose where you map your I/O. So in this case, we have these addresses that are given to us. All right, we have these addresses that are, oops. And then we basically just say, okay, I want to write to that address and that address that are given to us from the Vivado toolchain. And you can assign that in your own Vivado design. Are there any questions about how this works? Yeah. I'm pretty sure that usually in the compiler, if they don't see, like, if you don't specify that it's volatile, there's a lot of optimization that happens to make sure that your code is as fast as possible, especially on an embedded system like this, where you really are very limited by the amount of memory you have, right? I think in our processor that we'll use, we only have 256 kilobytes of memory. It's very, very small. And so typically the compiler is very good at optimizing everything. And I can't remember the exact reason, maybe someone here knows, but if you don't have the volatile keyword, sometimes it'll optimize away those signals, or those variables, and then you won't be able to use them. And it won't even like really throw errors. You just won't see anything happen. But that's because it gets compiled down to something that for some reason those variables don't exist. So I don't know, I would look into it, but there is a specific reason. It's because of optimization. All right. Is there any other questions about this? So the memory, where does our processor memory come from? We kind of just dropped in a microblaze and we didn't say, where is its RAM? Every computer has a RAM module. I mean, RAM is super expensive, so now we're limited to 256 kilobytes. So that's it. So yeah, I mean, if you have a bunch of these FPGAs, you get 256 kilobytes and that's it. But here, Vivado makes it very simple to set this thing up. You basically just drop the microblaze onto the what's it called? The block diagram. I mean, you can do it if you want now, but you just drop it on there and it'll say run block automation. It'll basically allow you to customize it, saying like, oh, I want my processor to have this much RAM. And it goes from 8 kilobytes up to 256 kilobytes. Very, very small. But this is, again, limited to how many resources we have on the board itself, which again, there are block RAMs on the FPGA fabric, but there's very, very little of it. All right. And so that's what we're limited by. And again, if we use all of our block RAM and we need more for our peripherals, then we're kind of screwed, right? I mean, we don't have enough. So by default, that's all we can do. We've only got 256 kilobytes. So how do we get access? How do we give ourselves access to more memory? Is there any way that we can do it, specifically with this board? Like, what do you guys think? Yeah. Well, I mean, if you can't change out the FPGA fabric, but there are extra peripherals on here that will allow you to use more memory. Okay, and I believe that there's a RAM. There's some external memory already on the board. So, again, as I said, the FPGA is just the FPGA. All of these things on the board, you have to manually connect them to your design. So there are peripherals on our thing that's already built for us. We just have to put controllers on there to access it. And there's external memory, and there's also SD card slots, I think. Yeah, there's an SD card slot up here, and then there's also USB slots that you can use like actual USB storage. You would just have to configure a controller saying in your design, maybe like a DMA controller saying how to access that stuff. All right. You have a question? Well, I mean, the FPGA itself by default does not have a CPU. That's right. Okay, and that's what I was saying. Basically, we implement a CPU, we emulate a CPU using the FPGA resources, meaning lookup tables, and it actually works like a normal processor. So you interface with it just like any other processor. Yeah. And so you can see here on the diagram, when you create the microblaze and instantiate it with a certain amount of memory, it creates all of these controllers for you. You don't even have to worry about it. It just does it for you. But if you want to add extra memory, which you might if you do a very complex project, then you have to either use IPs that already exist to interface with the USB slot and then stick a USB into there so that you can get access to a lot more, or the SD card. And again, because the main memory is only 256 kilobytes, if you remember from class, main memory is only 256. When it's pulling data from other places, like let's say an SD card or a USB, it's not actually expanding its main memory capability. It's kind of using those as swap files. So it's taking stuff from the USB, bringing it to my tiny 256 kilobyte memory, and then using it, because that's really the only place it can use, can access memory. So it's going to be pretty slow in that sense because you have such a limited main memory. And this is, I mean, again, if you built computers, you know this is why you want usually more RAM to an extent, right? Because it gives you, there's less swapping of memory from main memory. It just makes things a lot faster. But we're limited to this. For an embedded system, this is actually pretty good. I don't know how much memory they used building the lunar stuff going to the moon in the 1960s, but it's probably less than this amount of this amount of main memory. So knowing that, we should be much more efficient with our programming. You have to be when you're designing an embedded system, because we just don't have infinite access to RAM, right? So here's an example of just a whole system that you might see. This is basically a design that I made just this morning, putting a microblaze on and then adding some components here, which are AXI components to access the switches. I think the switches are here, the LEDs are here, and then having a module for UART. And you can look at the resource consumption on the bottom left. Look at how many lookup tables are being used. I think it's like 1% or 2%. So look at that. So we have a whole processor system. We have AXI modules. We have block RAM being used. Of course, the BRAM, there's a lot of it being used. I only used like a minimum amount that I could, but you see it's very low usage. So that's really good for us because now we have a lot of space to add really complex designs. Like let's say you wanted to put a machine learning model on your FPGA, you could because now you have a lot more space to do it. And you can have this microcontroller that can coordinate everything for you. So even with a full processor, you'd think it would take up all the space. It doesn't specifically if we use this type because it's optimized for this type of FPGA usage. But in a bigger system, like let's say, I think some of you guys have boards that are like using a Zinc 7000 or something like that. Those are FPGAs, but inside of the fabric, you'll actually, I mean, you obviously can't see it, but there are two ARM Cortex cores under there. And so you don't actually have to, you don't have to instantiate the processor like this. The processor will get mapped directly to that ARM Cortex core. It won't use any lookup tables, won't use the BRAM because that stuff is there. But of course, what do you think? It's going to be more expensive, typically, right? Because you have more resources. So we just have to settle for the fact that we don't have a real SoC in an SoC class. But you guys know how to design a custom SoC. This is it. This is like the simplest example that we could do. This is an SoC now because once I load this onto my board, there's a processor now, and there's access to GPIO, and I can program that processor that's running on my FPGA, and it'll work just like a normal processor. So now we really do have an SoC. So people keep telling me that this isn't a real SoC board. We can make it into an SoC, all right? Because what is an SoC? Has a processor, has memory, and we can control peripherals, all right? All on the same chip, and we've got that. We've got that now. And you can see, like, even when I mapped it, I kind of covered some of it because when I did the implementation for this specific FPGA, there was basically like very little being used up here and then all down here, but it's so little compared to how much resources we have. So that's really good that our processor is so small. So when you guys design your final project, you will be able to do much more complex things. And this is a bare metal implementation. So what does that mean? It means that I'm just writing direct C code that controls hardware directly. But a more advanced way of using microprocessors is actually running operating systems on them. Most embedded systems now, like if you get like some development boards that already exist, if you plug them in, you can usually like SSH into them, connect Ethernet cables to them, and control them using, and access them via a Linux interface. And we can do the same here. Surprisingly, even though this FPGA is so small, or sorry, the microprocessor is so small, we can put a version of Linux on there. And that's what you guys are going to do in project 3. So first, project 2 is going to be something like this, and then more advanced peripherals. Project 3 is then putting Linux onto your microprocessor that you've already instantiated, and then using maybe a higher level language to control stuff. So I could literally write Python code and control the LEDs on this FPGA, on our custom SoC. We can use Python, which is great. I mean, it's going to be slow, but you can do it. And for your final project, those are the types of things that we want to see. So for the final project, remember, we want to have the microprocessor. We want to see that you use some type of operating system, an embedded operating system. Usually this is in the form of PETA Linux. This is a Linux distribution that's designed just for this type of use case. Again, but you can choose to do whatever you want. And then, we would want to see some type of network connection because, again, there are Wi-Fi cards on the board. We would like to see that you could control peripherals or whatever you decide to design using a remote machine. So that would mean me having my board here, and then I'm writing some stuff or sending commands to my board, and then it does something. So keep that, yeah. Well, the main difference was that the Urbana board, I mean, specifically, it just uses, really the most important thing is the FPGA that's on it, right? The FPGA is what dictates what type of power we have, because all of the stuff around here are just components, hardware components that we can access, but aren't used unless we decide to. The FPGA itself is the thing that really defines the board's power. And this FPGA specifically on the Urbana does not have any embedded processor on it. So like imagine like, there are real microprocessors that you see in computers. This one does not have that. So you have to use some type of emulation technique, such as using a soft core processor to get that type of behavior that we would want to see. Like we want to be able to program our stuff. So we have to use a soft core processor versus other boards like the Pink and the Zybo boards, for example. They use like a Zinc processing system, which is an FPGA plus processors all on the same, like in the same little square. It has the processors and the FPGA side. So there's a reconfigurable part, and then on the actual fabric, there's processors. So when we put processors on the schematic, when we say, oh, map this to the board, it doesn't map it to lookup tables, the processor. Rather, it just maps it directly to that giant processor core that we've already got on there. So it's just a dedicated resource for that purpose, right? So that's the main difference. Okay. Usually that's more powerful to have the processing system because it saves resources, obviously, but it's more expensive because then you have to manufacture a real processor. But there are advantages such as, it's going to be faster and it's going to use a lot less power because, again, ASICs are designed for a certain purpose and they're going to be much better for one specific application. Right? That's what they're designed for. So, are there any other questions about what we've done so far? So once you have designed your custom SoC, how do we actually program it? Right? We know that we've got some memory on our processor. Well, we've said to use the block RAM, but now we have to load instructions into that. And so you saw I had some C code over there, but how do we actually get that there? You're going to use a tool called Vitis. I don't know if any of you guys have used that. Have you guys used Vitis before? Some of you? You've used Vitis? I don't know what Vitis AI is, but yeah. Yeah, so I mean, so when you downloaded the software for this class, you should have installed Vitis with it. I'm pretty sure that was in the instructions. And basically, Vitis is a tool. I think typically people hear about it as like a high-level synthesis tool where you can write C-style code or some other type of high-level code that gets synthesized into a hardware design. But what we're going to use is Vitis's embedded systems toolchain. So this is kind of separate. So there's the HLS side, which is usually what you've heard about, Vitis HLS. We're going to use Vitis itself, which is a software that's built on top of Vivado that allows us to program our embedded FPGA, our embedded microprocessor on our FPGA. All right. So when you make your design in Vivado, it allows you to specify where you want the memory addresses of each component of each peripheral that you make. So let's say I instantiate some LED GPIO component in my design. Well, Vivado will automatically map it to some place, some region in our 256 kilobytes of memory, or however much memory you've got. It'll do that for you. Now you can choose where you want it, I think, but usually it's just easiest to just let it decide for you. So it'll give you some region of memory and it'll put it there for you. So you send your design from Vivado to Vitis, and it basically just maps everything from it takes all your peripheral addresses and turns it into some header files that you can use in your programming. Because let's say I want to write to an LED address. I don't really want to go look at the actual number. I just want like kind of like a variable thing where I say write to LED address. Right? That's a lot easier. So Vitis will create all these header files to do that for you. And that's very powerful. And any C code that you use, you basically have to import that file, and it's called X parameters. It's usually not included by default. I'll give you guys a tutorial on how to do that stuff. But you have to import it, and then you can look inside the file, and it'll have memory addresses for everything. Because again, a microprocessor is not just the peripherals. There's a lot of other stuff, a lot of other regions of memory, but all you're going to be focused on is where did my peripherals, my AXI peripherals get mapped to, so that I can write to them or read from it, etc. And the C code that you write is going to get compiled down with the Microblaze toolchain's GCC compiler into a thing that's called a .elf file or an ELF. It basically contains all memory addresses, machine instructions, the text section, like etc. It has everything that you need to program it, and it'll basically send that down to the microprocessor via the UART cable or the JTAG cable, and it'll send it in there. It'll go into the memory and program it all at once. So it basically combines your hardware design, combines the software that's been compiled down, and then programs it all at once, such that as soon as your board turns on, it'll have the processor and it'll be running the code that you've got there that you design. All right, so that's basically all you're going to be doing in the next lab. So looking forward, what we're going to be doing is we're going to learn how to create AXI components. So again, I think has he started teaching about AXI? But I think he's about to get into it next class. So again, AXI is similar to the AMBA protocol. AMBA is a protocol made by ARM that just allows you to connect to peripherals. AXI is another, I think it's also from ARM, but it's another type of protocol basically that allows you to connect peripherals. It's just faster than AMBA. But you're going to learn how to design components that can interface with this protocol. It's going to be relatively simple, and you don't really need to understand the nitty-gritty of the AXI protocol to actually design something that works with it. Because usually Vivado, you can create an AXI peripheral, and it'll give you a lot of the starter code that handles, decoding requests from the AXI bus. You'll also learn how to write software to control the real hardware components on the board, similar to what you did in microprocessors. This class is basically a microprocessors class. So that's why the main prereq for this class is MicroP, right? Because the main thing that you're going to be doing is writing C code. So if you really think about it from what you guys learned before, MicroP gives you a processor that's pre-built, has all its peripherals. I mean, it's got those backpacks and stuff, but they're basically pre-built components. Now you have to design all those peripherals and how they connect to each other. Because again, when you did it in MicroP, you just wrote to an address. He just gives you a header file. You're just given a header file and you just know where to write everything. Now you get to choose all that stuff. You get to design your custom microprocessor. So that's really the power of this class, and then it's all going to be on the same chip. So yes, there are some peripherals that are off the chip, like there's the LEDs, the switches, etc. But let's say you want to design a hardware accelerator. That will be directly on the FPGA fabric. So that really is a system on chip. We just have some extra peripherals here because there are some things that are too complex, like the Wi-Fi controller and stuff. We want to have access to that because it's a dedicated component. We don't want to waste our precious FPGA fabric, our lookup tables and stuff on implementing all that type of stuff. Now, I mean, some of this stuff you really can't design, like these header pins. That's to interface with other components that you want to use. And obviously all the logic that's controlling that is on the FPGA itself. Next, you'll learn how to load up an embedded OS, basically Linux onto the microprocessor that you've put on there, and then use other languages such as Python or Rust or whatever you want to do to program it. It doesn't have to be just bare metal C, because typically when you're designing code, I mean, you can do that, but there are other ways. And you can also use the Linux file system, because when you put Linux onto your microblaze and stuff, it'll actually map those. Again, if you have experience with Linux, you'll know that if you write to specific files, everything's a file in Linux. So if you write to specific files that are mapped to your hardware component, you can actually just write like a 1 to this file, and it maps directly to an LED on the board. Right? So everything is a file in Linux, and that's something that you'll also get experience with. And then for the final project, has anyone started thinking about what they want to do at all? Anyone thought? It's a little bit hard when you don't know, or if you haven't seen everything in this class yet, but all I want to see for the final project is that you use all of the stuff I just talked about here. And you can see that it's pretty general, right? So all you need to do is just have a microprocessor on there, have AXI peripherals, and then have an operating system running on there. And then ideally doing some type of network connection via the Wi-Fi chip, which again, you don't have to implement yourself. There are IPs to help you do that. But that's what you need to start thinking about for the final project, because I'm looking to like finalize that stuff around February 20th. So if you want to do your own project, I think you need to propose it to me by the end of February around this time, because if we start too late, I mean, we're just not going to have time to finish. Because the typical project in this class was the robot car or the self-driving car. I don't know. There's something like that. I did not do that when I was in this class, but the problem with that project is, I mean, I'm sure some of you have heard about it. It's too hard. It's too complex because you have to design everything. Like you have to connect the motors. You have to design the RTL to control the motor. It's like very, very hard. But it doesn't have to be that hard. I just want to see something, more unique. And I linked like on the announcement that I posted about the final project groups. There's some examples there's an MIT class. It was their digital design class, but somehow their digital design class is more advanced than like our class too. So, I looked there and they had a lot of cool stuff. And so you can look there for just some inspiration, but it can really be anything. A lot of people did image processing. So what you can do is you can probably, I don't know if we have cameras or not, but you can buy like a small camera that interfaces in these PMOD connectors, and you can just hook it up, and then you can, write some code, do some image processing on it. I saw some examples of people that did like a live Photoshop thing where it's like you have an image that's displayed on a screen and you'd flip some switches and it would change its color, move it around, like literally hardware accelerated image processing. And if you do something like that, that'd be pretty cool, because that's like a very good application of computer vision. You can also do machine learning applications on FPGA, like just doing hardware acceleration on the math that needs to be done to do inference on certain machine learning models. So that's something that you could do. But again, start thinking about it. And especially if you haven't gotten to a group yet, I think you need to start doing that, because it'll be hard if you join last second with someone else and then you're either forced to do the final project that's given to you, which again, that's also linked on the announcement if you haven't seen it yet. So take a look at that. And if you haven't, I will just say, I think it's going to be much less satisfying to do the project that is provided, because it's more so just a survey of everything that we do, but there isn't really much coherence. It's not a project that you can put on your resume, but I want to give you guys the option to do that, right? I want to give you guys the option to come out of this class with a project that feels meaningful and something that you can actually show and say, hey, I could be an SoC designer. I could design like full systems myself. Because otherwise the final project that's given is just a lot less interesting, in my opinion. But again, you can go look on the announcement and see what you think about it, and then make your decision. So there's a discussion post on Canvas that you can ask other people if you want to be in their group, or if you have your own interests and you want to present to them and try and come up with an idea as a group, you can do that. But yeah, I mean, I don't really have much else other than that. I just wanted to give you guys an idea of what we're going to be doing. And hopefully it'll become more fun, because I know Dr. Bobda loves the theory, and that's really all you guys are going to be covering in the class. But my interest is more so in the application, And this is basically all your grade too. So yes, there is kind of a mismatch between what we're teaching and what we're learning, but I'm just trying to tie it back into what he's talking about. He's surveying everything about system on chip, everything that could be on a system on chip. But the reality is we have this type of board. But just remember that that type of those other more advanced processors, more advanced memory access stuff that is on other boards in real industry, gigantic FPGAs, gigantic boards, they'll have that type of stuff. And so if you were to get a job, there's a lot of people doing data center work now. They use FPGAs that are very, very advanced, very expensive because they've got all that extra stuff. This is such a weak FPGA board because it's designed for students for us to learn. But all that stuff really is relevant. But again, it is kind of hard to see that when the platform that you're given is not really matching what we're teaching. But that's the reason. So, are there any last questions before you go? Yeah. You don't need to. So I mean, when you design specifically in the project that puts an OS on the microprocessor, it uses a version of Linux. So there's an actual tool that will program it on top of Vitis. So you have to download another tool that only runs on Linux, by the way. So you have to use a virtual machine, but that will basically configure that stuff for you. So it'll connect all of your AXI peripherals and map it into files. Huh? No, it does. I don't think it works on WSL. Like, does it work on WSL? I don't think so. I don't. Hey, if you only have a Mac, I don't know. You just have to ask someone else. But it's kind of challenging to get it to work, even through virtual machines. You have to configure USB pass through all this other stuff. It'll be hard. So, what is it?
It doesn't work on the other side.
I don't think it'll work on WSL. You can try it, but it is. I mean, it is. But you have to download it directly from Xilinx's website, and sometimes it doesn't work. So, yeah, it's like Quartus. It kind of messes up. So, yeah.
Yeah, it's available on Ultra Skill Plus.
Yeah. Well, we don't have that. We don't have that stuff. So.
I mean, I haven't thought I gave it back. I should have kept it honestly. Because but it's I meant for like data path testing. Like you can run a whole bottleneck simulation with a